C'est vous qui voyez. Bah, à la limite, on peut laisser le micro.
Welcome to all. Okay. Okay, we are starting the event at 9:30. It's 9:30. Just a couple of words. I'm Gunay Ndirim from CEA Bordeaux, and I'm involved on the Astrabat project with my colleague Yolande Murat as coordinator. And thank you, Yolande, for the organization with the other project. And just to introduce my colleague, Yves Samson, program director in CEA Bordeaux. And following your presentation, Simon Perraud, deputy director of CEA 10 and also a member of the executive board of BEPA for BEPA presentation. And welcome again for all.
Thanks a lot. So indeed, my name is Yves Samson. I am Program Director of CEA Technological Research Division. That's really a pleasure to host you today for two reasons. The first one is that Europe is really a key playground for CEA, and everything we can do with you, both industrial and academic partners, is really important for us. The second one is the topic of the meeting. Batteries are obviously a key part of the energy transition, and that is one of the major commitments of CEA, as you will see within a few words I am ready to give to you. So thanks a lot for joining, for accepting to be in Grenoble today. So the CEA was founded in 1946, so roughly 70 years ago, with a very clear mission, almost unchanged since the beginning, that is to serve the state of the citizen. And we have both basic research, but mainly technological research in 4 areas. The first one is low carbon energies. Now in France, we are very conscious. We have to go very fast. We will almost lack of energy. So we have to develop both nuclear energy and renewable energies, and obviously batteries to serve both. Digital technologies, specifically in Grenoble, we have very strong asset in this domain, with CEA Leti, for instance. Health technology and defense and security, building upon our technology from nuclear energy, for instance. A few figures. So the CEA gather around 20,000 people, permanent and non-permanent staff. You have the budget in the left corner, sorry. As say, we are very focused to create value for society, and the main mean to do that is transfer to industry. So you see, we are filing a lot of patents each year, typically between 600 and 700. We have a very large number of industrial partners, and this means we normally rank very well in all innovation ranking at European and international level. Practically, we are only on a few sites in France. We have 4 large sites for civil application. One source in Paris, connected to University Paris-Saclay, one in Grenoble, connected to University Grenoble-Alpes, and 2 in south of France, in Cadarache and Marcoule. We have 5 centers dedicated to military application, and a few regional locations, red one, with small teams that are dedicated to bring our technology closer to small companies, medium-sized companies that may be too far from us to benefit without these neighboring facilities. Now I will focus on our technical research division. Roughly a quarter of the CEA, as you see, but obviously a strong focus on transfer to industry. This can be seen from the budget, only a quarter coming from subsidies from the state, and the 75% remaining almost split between direct industrial contract and institutional contract. This means we have roughly 200 million of euros of industrial contract direct each year. Obviously patents, the need to invest a lot, you will see why in a few slides, and we are both creating startup and having direct link to industry. To be able to transfer, and this is very important for batteries specifically, but also in other areas, we need to have tools very similar to the one from industry, so that we are able to transfer the process almost directly to our industrial partners. We are not in basic research, we have very high-level basic research internally, but for technical research division, the goal is really to be able to be close to industry and to be able to transfer the technology almost directly. This came with large facilities for solar cells, for batteries, for nanoelectronics, and so on. For instance, in Grenoble, we have 10,000 square meters of clean room to be able to help the European microelectronics industry. I will go fast along this one, but you will see our main areas of investigation, obviously around energy. You can say hydrogen, batteries, solar cells, power electronics, that's very important, as this is connected to almost everything, and a lot of focus on eco-innovation and recycling of materials. That's really a key trend today, obviously. This can be connected to our asset in the digital transition, for instance, artificial intelligence, factors of the future, some parts of microelectronics, also artificial intelligence, and maybe used, for instance, to monitor and pilot batteries. And a lot of asset also in cybersecurity that is so important, for instance, for electrical network that are very sensitive now that they are more diverse and disseminated and not really linked to energy. Some very high-level activities around health technology, not really medicine, but health technology. As said, we are working a lot with industry at all scale, at all level. In France, we are working with large companies, mid-sized companies and SMEs, adapting our partnership to the needs of each kind of partner. At international level, you can see here some names, some are confidential, both at European and out of Europe level. And that's also very important, both to help the European industry, but at national level to remain competitive, because we have sometimes some demands from industry that are very challenging, and this helps us to prepare new technology and to be able to transfer something to tomorrow. We are organized with so a small institute in region in France, but 3 large institutes. Simon, who is the next speaker, is the deputy director of CEA-Liten, and CEA-Liten, with the blue parts here, is really focused on the energy transition, with part on some technology I already described, I will go fast, and some on materials and nanomaterials. And they obviously benefit of cross-fertilization with other technology pushed by CEA-Leti and CEA-List that are more on digital transition, both on material and software. Last, you are now in Grenoble. We are in this part, out of the photography, so embedded within the mountains. But what I would like to say is that you are a very significant campus with both technological, basic research, training, university institution and so on, and also large instruments. To be clear, more clear, here you have the CEA, here you have the European campus. We are lucky enough to have on this side the European synchrotron facility and the European neutron facility, Institut Lowe et Langevin, and we have very active partnership with both, including to characterize batteries, for instance. We have a specific partnership with the European synchrotron research facility for that. Also, we have basic research, both from CEA, from CNRS, and from university, including connected to your field here also. On this part of the center, we are here. We have all our research for energy, but also a large school of engineering for energy, what we call NC-Cube. And on this part, we have the research on digital technology, including the clean room. And once again, a very significant school of engineering focused on materials and microelectronics, FELMA. You can see the figure, so it's really a cluster of competitive partners working together in research, training, and innovation. Maybe a few words. You are already partner to some extent of us. We are a research technology organization. What this means can be found in this joint report from the OECD and ERTO 2 years ago now, almost 2 years. We are evolving in our model. We used to be working in very high confidence in a bilateral ways between CIA and a company. We are trying to diversify the model. This remains really true. But for instance, this is now very advanced in microelectronics, but I am sure it will come also in the field of energy. The European Commission is funding some facilities to increase European competitiveness. And this means we have to work with other RTOs, for instance, maybe someone from Fraunhofer in the room, together to serve the European industry, to serve European competitiveness. And we may work together to serve in a bilateral way some company. Also, and this is specifically true in France now, in the frame of what we call the competitive plan launched after the COVID crisis, we have some national funding helping to address some technological challenge. And very often this means we have to work in this frame with many companies in the same way, what we call in France industrial filière, that is to say the gathering of companies working in the same field. And so this means we have new challenges to implement new ways of collaboration. Last slide before concluding. We are willing to serve societal challenges. This means we have to understand the uses of technologies better than in the past, and not only to push some very bright, maybe, technical idea we may have. This is partly, you can see this large building here. This is the other side of the building. We have a full department dedicated to that. We have a technology hub. A hub is a place, a virtual place. They are coming where many industrials are working on the uses, future uses of a given technology. For instance, we have one on quantum technology. We have one on defense application. We have one again in circular economy. This is collaborative, and this is the best way to try to imagine what could be the future for a given technology. And so we try to have both the vision of the technology of tomorrow, but also the uses of tomorrow to design the best offer. Last, thanks again for joining us in Grenoble. This is a picture of the CA Lytton facilities for batteries. And I'm not sure you will be able to visit, but feel free to ask, I think, today or another day. Thank you again for coming us.
Hello, good morning. Very glad to be here with you today. So my name is Simon Perraud. I'm Deputy Director of CEA Lytton, one of the institutes that Yves just presented. But this morning I will not talk on behalf of CEA, but on behalf of BEPA, which is the Battery European Partnership Association. And I will, in this presentation, explain you what is BEPA and what is the Batteries European Partnership. So, yes. But for you, this Batteries European Partnership is a partnership under Horizon Europe between two parties. On the public side, the European Commission, and on the private side, an association called BEPA. And the main goal of this partnership is to establish and implement a research and innovation program under Horizon Europe on batteries. there are two parties in this partnership, and there are some, let's say, some commitment from the two parties. So from the public side, from the European Commission side, there is a commitment to fund around 925 million euros for batteries in Horizon Europe. And from the private side, from the BEPA side, there is the commitment to have the same amount of money, so around 900 million euros, devoted to batteries with private funding, coming either from companies or from research organizations and universities. So this kind of commitment creates a leverage effect, and in total it means that around 2 billion euros of funding for R&D, research and innovation on batteries will be available during the 7 years of the Horizon Europe program. So what are, let's say, the main objective of this partnership? The first objective is to support the industrial value chain in Europe. So as you know, let's say since 2017, 2018, there has been a lot of developments in the industry in Europe in the field of batteries across the value chain. In the media, we talk a lot about battery cell gigafactories, but there are also other sectors of the value chain which are developing quite fast. Materials, recycling, and of course electric vehicles and also stationary application. So the main goal of this European partnership is to support this industrial ecosystem, and to do that, the aim is to provide the industry with competitive technologies. And if we go in a little bit into the details, the specific objectives of the partnership. So first, providing these technologies to the European battery industry across the value chain, materials, cells, battery packs and systems, and recycling. Second objective is to address the mobility market, electric vehicles, but not only, other forms of mobility in road transport, but also waterborne and airborne transport. Because as you know, the main driver of the battery industry today is electric mobility. And the third objective is to address the other large market, which is stationary storage, to enable the integration of renewable energies into the electrical networks. So this is what we address in these partnerships in terms of research and innovation. So we work on materials, raw materials and advanced materials. On battery cells, we have also some important activities on packs, modules and systems, battery systems. We have also some activities on integration of batteries into different applications. But for that, we work with other partnerships which are established in Horizon Europe. So for example, 2.0 for the road transport, or the waterborne partnership for waterborne transport. So let's say the end part of the value chain, the downstream part of the value chain, this is something that we are not doing alone, but we are doing in collaboration with other partnerships inside Horizon Europe. And finally, we work a lot on end of life, especially recycling, which is absolutely crucial today. This is a little bit of a commercial slide to invite you to join BEPA. So BEPA, the association, is managing different working groups. joining BEPA is also a very good opportunity to network and to meet colleagues from other research centers or from industry. It's also a big opportunity to access to information on the battery industry and on the battery research and innovation field. And also, it's a way for the stakeholders joining BEPA to participate to the elaboration of the work program in Horizon Europe. So today we have more than 200 members in 25 countries. There is a good match between industry members and research members, and we have also around 40 associations which are also members of BEPA. The working groups. So this is really the core of the, let's say, the core activity of the BEPA association. And these working groups are managed jointly with Batteries Europe, which is a technology platform, the European technology platform on batteries. And in the next slide, I will explain you how it works between BEPA and Batteries Europe, how we share the workload. But first, let me talk briefly about this working group. So these working groups, they gather experts. Typically, it's between 50 and 100 experts per working group to discuss about research and innovation roadmaps and to participate to the elaboration of the work program, the Horizon Europe work program. So the working groups, they are divided according to the value chain, so no big surprise here. Working group 2 is devoted to raw material and recycling. Working group 3 to advanced materials, so active materials mainly, cathode, anode, but also electrolytes. Working group 4 on cell design and manufacturing. And the working group 5 and 6 are devoted to the main application that I was mentioning before. So mobility application for working group 5 and stationary application for working group 6. And there is also working group 1, which is devoted to new and emerging technologies. So this is something which is more, let's say, for long-term research and very advanced technologies. So how it works? There are 3 main steps in the process. So the first step is and these three steps, they involve the 6 working groups that I was just presenting. So the first step is managed by our colleague from Batteries Europe, is to establish the roadmap. Actually, the roadmap, the new version of the roadmap was published, I think, yesterday or the day before yesterday. Maybe you have seen the news. So this is the first step, and this roadmap, it's a research and innovation roadmap. The goal of this roadmap is to be quite inclusive, so to highlight what is the state of the art today, what are the main objectives of the battery sector, and what are, let's say, the technological gap that we need to fill. So what are the main strategic orientation for battery research and innovation. So this roadmap, let's say the spirit of this roadmap is to be quite inclusive and to cover, let's say, the full field of batteries. Then once the roadmap is established, the next step is to establish this SRIA, which means Strategic Research and Innovation Agenda. And this document is under the responsibility of both Batteries Europe and BEPA, together with the European Commission. And the SRIA is, you can see that as a kind of zoom. So the idea is to take some key topics inside the roadmap and to say, okay, among all these topics described in the roadmap, these are the topics that we need to focus on in Horizon Europe. It doesn't mean in Horizon Europe and especially in the BAT4EU partnership. So it does not mean that the other topics of the roadmap are not interesting, but maybe they should be funded under other partnerships in Horizon Europe or under national programs. So the 3A is a kind of zoom on the topics that we think are relevant for batteries in Horizon Europe. And then the last step is to draft the call topics, so the BAT4EU work program. And this is under the responsibility of BEPA. And at the end of the day, of course, the European Commission and the member states also are strongly involved in this process. And at the end of the day, it should lead to the BAT4EU work program in Horizon Europe. This is, I think, this is all. So, yeah, thank you very much for your attention.
Okay, I modified it just Thursday, but I modified it directly in the SharePoint. It's fine. No worries. Just to share. You have to do like this, and after it's quite important because the screen is like this right now, so this is not good. You have to go here and select this. But I can do it if you want. Okay. Okay, perfect. Thank you. Okay, so good morning, everyone, and thank you for joining this event. So my name is Maria Martinez. I'm coming from CIC Energigune in the north, a research center in the north of Spain. I'm today here representing SAFELIMOVE project. So we are going to already start introducing the cluster and the different topics that we are covering. The agenda will be, so we will have 1 hour and a half for this session. I will start with a brief introduction to the general cluster, so the motivation of these 4 projects. And later we will go through the different projects. The coordinators will be presenting the latest results of these 4 projects that were granted under the same call. And finally, we will have around 10 minutes for questions and answers. So please gather all the questions that you have during these different presentations, and then we will have some time at the end to discuss all of them. Okay, so as I was saying, I will start briefly introducing the clusters. So this LCBAT1 cluster is a strongly improved, high-performant and safe all-solid-state batteries for electric vehicles. And of course, I would like to highlight, before going on the details on how each of the projects have been addressing the challenges of solid state, I would like to provide an overview of the motivation of this call. So through this call, the European Commission wanted to develop higher energy density solid-state batteries, of course, highlighting the safety issue. So this is one of the key parameters that we need to address within the different projects. And the aim was to go beyond the state-of-the-art solid-state electrolytes, where we have, as you may know, inorganic, polymeric, and hybrid electrolyte. So where this solid-state technology is classified, so here you can see, I think I have the pointer. Yeah. So here you can see the table where we classify the different technologies related to batteries. And in the case of the solid-state, it can be divided within 2. So actually, this call was covering 2 different types of technologies within solid state. So the so-called generation 4A, which is based on conventional lithium-ion materials such as NMC or silicon anodes. And then we have the so-called generation 4B, where in this case we are talking about lithium metal anodes. It's not working? Okay. Then this was the scope of the call, and here I'm summarizing some of the impact that I'm pretty sure that you are well familiar with all of them. So the Commission was looking for high energy density, as I was saying before, both gravimetric and volumetric. And in this case, if we consider generation 4A, the targets were beyond 350 watt-hour per kg and 1,000 watt-hour per liter, while on the other hand, in the case of 4B generation, we are talking about values above 400 watt-hour per kg and 1,200 watt-hour per liter. So of course, these are really challenging values that we are trying to target within the different projects. Another impact that is expected or outcome from this cluster or from these projects are fast charge to address the demand from, of course, battery electric vehicle users, proven safety, the reduction on the cost below 100 euro per kilowatt hour. And of course, we also want to strengthen the value chain in Europe by means of the solid-state battery technology manufacturing, proving also this prototype into a pre-industrial environment. And at the end of the day, we need to consider when we are developing this technology, all the recyclability of the materials. So we needed to go through a thorough life cycle analysis, cradle to cradle, in order to have in mind of this parameter. Even if when we were preparing these proposals on the earliest stage or how the solid-state batteries will be, we needed to consider all this in advance. And just before going to the details, as I was saying before, I will show to you how these projects have been working as a cluster. So we have been covering different points of the whole value chain. So mainly, we are aligned on covering from the material sourcing, material processing, cell component manufacturing, cell manufacturing by itself, and in some of the projects we have been also working with the VMS. And then at the end of the value chain, we can see that somehow we have been trying to address recycling. Tomorrow you will see in the topical session related to sustainability and recycling how these 4 projects have been working on these 2 key topics and the results and the outcomes that we have from the 4 projects. And then, if we take a fast look to the 4 projects, so here are just some highlights because I would like that you have clear the similarities and the differences. So we have Astrabat, that is coordinated by CEM, SAFELIMOVE, coordinated by CIC Energy Gune, Solidify, coordinated by IMEC, and Sublime, coordinated by FEV. So you can see that all these projects are not, of course, here is summarized who is the coordinator, but behind all of them, there are many different partners, so roughly between 14 and 15 organizations from many different countries in Europe and beyond. The project length, here I will say that later will be updated because I think that some of the projects has applied for an extension, but roughly the call was asking for projects with a length of 48 months, more or less. Most of them were started in January 2020, except for Sublime, that it started in May 2020. And you can imagine that we are reaching the end in most of the cases of these projects. For that reason, I'm really glad to have everyone here again, because I was just before discussing that it was like kind of 2 years ago when some of us, Astrabat, Solidify, we met in Brussels. So we were in the earliest stage of the projects, still not many results, just foreseeing how it was going to be. So now after more than 3 years and a half, I think it's really good to meet 4 projects together and really see, not only see the outcomes of the results, but also discuss on how is going our experience, the main challenges that we are facing with the solid-state technology. And here is summarized how these 4 projects, the chemistry, cell chemistry that they are using. So in most of the cases, we can see that there is a common parameter that is the cathode, where we are talking about NMC. Then on the case of the anode, most of the cases is lithium metal. Of course, there are some differences on the type of the lithium metals and strategies that we are using. where we have Astrabat, that is the most different strategy or cell chemistry on this regard, where they are using silicon-based anodes. And then for the electrolyte, again, so as we have seen before, solid-state electrolyte can cover many different chemistries, so inorganic, organic, hybrids. And in most of the cases here, we have been focused on polymer-based or hybrid-type electrolytes. And on the other hand, we have Sublime, that they have been based on sulfide-based electrolytes. And then by means of the TRL, the call was asking for a TRL of 6. So in most of the cases, we are around 5, 6 TRL. And this is translated into a demonstrator with a capacity between 1 to 10 ampere hours in most of the cases. So of course, here is what it was designed at the very beginning. Later, we will see what is really what we are in the different projects. And then by means of sustainability, both LCE and recycling have been considered within the different projects. We have seen that some of the projects have been focused more on one of these points. But as I was saying before, so today we will provide some details about the different projects. And then later on during the different topical sessions that we will have, we will go more into detail by means of how manufacturing has been addressed within the different projects, or sustainability, recycling, modeling. So we will have time to really know more the details of the different projects. And here, just sharing some information for the different projects, our websites where you can find all the details, the results, the publications, all the outcomes for these 3 years and a half. Of course, you can follow us on Twitter, on LinkedIn, so please go through it and visit our websites. And this was all from my side for starting. I will be back later for SAFELIMOVE. Now I give the floor to Sophie, that she will be presenting Astrabat project.
Thank you, Maria, for this presentation of the different projects. So now I will present more particularly the Astrabat project. So Astrabat means all solid-state reliable battery for 2025. So the key figure also has been already mentioned previously, but effectively in Astrabat we cover with the consortium all the value chain associated to the development of all solid-state battery, with some manufacturer of material for lithium-ion battery, such as nanomakers for the silicon, and Deakin for polymer, Umicore for NMC materials. We have also some industrial partner for the battery manufacturing, Leclanché and UNESCO, and also 2 partners for the part related to end use, such as ELAF, that is a small car manufacturer, and Stellantis, that is developing electric car vehicle. So now I will more focus on the objective of Astrabat. The main objective of Astrabat effectively is to find a better cell architecture for solid-state electrolyte. The idea effectively is to design the electrolyte in order to validate some safety properties, and also all the part related to energy and power characteristic. For this purpose, we develop new electrode materials. So it is the first objective of Astrabat project in this frame. And the first result that I can present to you today is effectively related to the key performance indicator related to the ionic conductivity of electrolyte. In Astrabat, we work with hybrid electrolyte, considering anolyte for the anode side where we have a silicon electrode, and catholyte with some PVDF base material for the NMC cathode. The idea is to find some material that, as a cathode side, is able to manage the head voltage, and at the anode side is to find some material that is able to manage the different modification of volume of the silicon during the charge and discharge. The second point that is important to consider is also the safety. In the previous slide, I showed that we have some polymer electrolyte. In order to improve again the safety, we need to reinforce the structure of the membrane. And in this case, we have decided to work with some ceramic conductor, such as LLZO powder. In this case, it is a Fraunhofer that has developed some LLZO. We reached the conductivity that has been targeted for the key performance indicator with 3 millisiemens by centimeter. And we have developed at Deakin some composite materials based on the catholyte, in this case PVDF base with the LLZO. In order to go also to different properties for thermal stability and also the process of the material, partner of the project WUT has developed some new lithium salt. And in this case, we have a series of different lithium salt that has reached the target that we have defined for unique conductivity. The next objective that I would like to consider is a processing technique compatible with large-scale manufacturing. In this case, effectively, as I mentioned previously, we have different manufacturers of product powder, silicon powder, and NMC powder that has been integrated inside the development of Astrabat. Here you can see some development with Nanomaker, the silicon, and Fraunhofer has also worked on the infiltration of the Hormoser anolyte inside this type of material. This afternoon, you will see a presentation dedicated to this, and also to this result where we have directly managed the process in order to manufacture after the anode electrode and the electrolyte. And then, effectively, we would like also to consider pre-prototype, and in this case, we clearly validate the process on a pilot scale size. As Yves Samson has shown previously, as a CA, we have different equipment very close to the pilot size. And all the electrode developed in the Astrabat has been done on this type of pilot in order to have reproducibility and well-controlled thickness of materials. Here you can see some laboratory development for the process related to the membrane manufactured on the electrode side. And we have obtained and developed clearly the full electrode and the full cell. The first results are reported here, where we can see that we have a large decrease of capacity at C/10 and C/2, but it is the first thickness that we have managed. We need to decrease again the thickness of the electrolyte. But we have got a good stability of cycling, and after we can have again the capacity of the material on the cell. In Astrabat, we consider also the next generation of the electrode and on the cell architecture, and in this case, we would like to improve the cell design, and based on this, we have developed some model to see exactly where we need to put the cathode and the anode, and we have developed some tests and some formulation of ink in order to be able to manage this in additive manufacturing. So the problem at the moment is effectively to have the formulation of a suitable ink with keeping the same characteristic of the material, due to the fact that we need to decrease the particle size in order to avoid nozzle clouding. Sometimes we decrease the performances of materials. And the last objective is related to the recycling and the eco-design. In this case, all the work related to certification and considering also standard has been done. And we have also developed LCA in order to validate the impact on the environment of the different solutions that has been considered in Astrabat. So I let you this last information related to the handbook of Astrabat that has been submitted last month. And thank you very much for this.
Thank you, Sophie, for introducing Astrabat. And later, just a reminder, we will have time for question, okay? Maybe, actually, I was checking, maybe we are in time, we can even have time for questions, no? Or do we continue? It's until 10:30.
Yeah, depends on you, how much you take to present.
Okay. Okay. So, good morning again. Now I will continue. This time I will be introducing SAFELIMOVE, the project that I'm coordinating, actually, from CIC Energy Gune. And SAFELIMOVE stands for Advanced All-Solid-State Safe Lithium Metal Technology Towards Vehicle Electrification. So here, as I was saying before, today you can see my face here presenting this project, but there is a lot of people behind and many partners working on this. So we are covering the whole value chain from universities, research centers, and technological centers towards end users and also industrial partners. So here I'm just summarizing, you can see all of them. We are 15 partners coming from 7 different countries, most of them from Europe, but we have also Hydro-Quebec from Canada. Actually, Abdel is here today with us. And, sorry. And as I was saying before, the length of the project is 48 months. It started the 1st of January, so we are going to finalize the project by the end of this year, the 31st of December. And the founding budget was 7.8 million of euros. Going to the overall objective of SAFELIMOVE, so before I was summarizing the objective of the cluster as a whole, but of course this later has been addressed by different ways. And here our target is to reach high energy density, as I was saying before, for the GIM 4 billion batteries technology is above 450 watt-hour per kg and 1,200 watt-hour per liter. And in order to reach this target, we define different objectives. For the cell chemistry, we define high specific capacity lithium metal anode, going to thicknesses below 50 micrometers in order to be able to meet these values of energy density. For the cathode side, we were looking for high voltage active materials, mainly nickel-rich layer oxide cathodes, where we have a voltage above or around 4.4 volts. And then we have the electrolyte. In this case, our strategy was to combine the best of both phases, so inorganic and organic. So for that reason, we decided to work with a hybrid ceramic polymer electrolyte, HCPE, aiming for high ionic conductivity beyond 10 to minus 4 Siemens per centimeter at room temperature, as well as high thermal stability to provide the safety of the battery, even if we know that the electrolyte is not the only part in the battery that we need to work with to guarantee the safety, and also looking for decreasing the battery cost. All these are the different components that we have been working with, but we need to consider also all the interfaces. So for that reason, there has been a lot of work on this regard, not only to assess these interfaces in solid state, but also to adopt them in order to have an effective lithium transport through the coating strategies. So the four main pillars of SAFELIMOVE are based, as I was saying before, on the innovative generation of materials. So we have the three main components: cathode, electrolyte, and anode. Then the advanced optimization of interfaces. We have been working a lot, actually, with CEA as partner on the development of in situ and operando techniques for the characterization of the interfaces. And then this also has allowed us to work on coating strategies by different means, as I will share before. And then another point, another outcome that the European Commission was asking for was to strengthen the value chain, the manufacturing of solid-state batteries. And we have been working a lot on this regard, and actually this is something that has been led by CIDETEC and SAF, that they have been the ones in charge of scaling up the technology. Later I will show that this has been one really challenging part of the project. And then the fourth pillar is related to the future market vision. So here we are including everything related to the cost model development, sustainability, recycling, LCE, and as well as the design of the roadmap towards 2030. So the methodology that we proposed at the beginning of the project was divided into four main phases. So we define phase one, where we have the development of what we call the level 1 material. Then this was tested in small cells, coin cells, and monolayers, and the feedback obtained allowed us to work on the development of level 2, that was used for the first generation of 1 ampere-hour cells. And in this case, as well, the feedback was used to the improvement of the level 3 material that was foreseen to be scaled up to 1 ampere-hour and 10 ampere-hour cells, finalizing the last phase with the building of the 24 volts module. Oops. And then, in order to design the technology that we were looking for by means of the electrolyte, we started to consider. So different environments in the cell require different type of materials. So if we are thinking on the cathode side, we really need to have a high voltage stability, while if we consider the lithium metal side, we really need to have a stable SCI formation. So we realized that it was not going to be easy to handle with the same type of hybrid electrolyte in both sides. So for that reason, we developed a V-layer concept where we wanted to have one type of chemistry in contact with the lithium metal and another type of chemistry within the cathode used as cathodite. And having all this in mind, we developed the first generation of level 1 materials. So based on the NMC 811, Umicore was developing the cathode active material. Then Hydro-Quebec was developing the lithium metal, and SHOT together, CIC and SHOT together were developing the level 1 hybrid ceramic polymer electrolyte. So mainly the level 1 materials were based on the cathode with a loading of 1 processed by CIDETEC with NMC 811, and the cathodite based on polycarbonates with LATP. Then for the electrolyte, we were looking for a polymer chemistry that is more compatible with the lithium metal interface, that is based on ether containing polymers combined with garnet. And for the anode, we had a 50 micrometer lithium metal, self-standing without the use of a copper current collector, which for sure has an impact on the final cost and the energy density. So the assessment of these materials by means of the electrolyte, we were able to have ionic conductivities close to the target of 10 to minus 4 at a room temperature. So the next step was to process all these materials and to manufacture what we call the Gen 0 pouch cell. So this was manufactured by CIDETEC, as I was saying before, and mainly the main motivation of this first generation of materials testing was to prove the compatibility and assess how people working on different materials, how we could bring them together and make sure that there was a compatibility and validate all of them. So here we tested in monolayers, as I was saying before. So here we have the performance for the first generation of all these materials. And the most important part is that the cycling was used to further understand how we could progress and develop and improve the performance of the materials. So post-cycling analysis allow us to really understand what was going on during the cycling, so we didn't have a really good interface between the electrode and the hybrid electrolyte. Also, we find some issues at the lithium metal interface. So with this guidance in mind, we work on the development of the level 2 materials. So the main challenges that we found in the cathode is that we really needed to increase the loading. We are talking about a loading of 1 milliampere-hour centimeter square, for sure far from meeting the targets for the energy density. We needed to improve the conductivity on the cathode side. We needed to improve the stability of the NMC 811, so we know that it is very reactive during the processing as well as with the other components within the cell. If we consider the electrolyte, one of the challenges that we found, actually was found by CIDETEC when they were trying to scale up, was the lack of enough mechanical properties. So this will have an issue on the handling, but also will have an issue when we are talking about the battery operation to avoid the propagation of lithium dendrites. And we needed to increase the unique conductivity. And then considering the third component, the anode, we needed to decrease the thickness because this will have an impact on the energy density, but also we were looking for improved interfaces stabilities. So for this, the strategies that we developed, so for the cathode, we decided to go directly straightforward towards a really high loading of 3 milliampere-hour centimeter squares. We work on the conductivity through different additives, and then Umicore also work on the development of the coatings or different coatings for the NMC 811 active material. On the case of the electrolyte, we needed to improve the mechanical properties, as I was saying before, so we decided to go to a cross-linked polymer network containing the inorganic filler, and also the addition of safe plasticizers, a small amount of oligomers, polymeric oligomers, in order to increase the unique conductivity without sacrificing the safety of the electrolyte. And then on the case of the anode, we decrease, again, without any copper current collector, we decreased to 40 micrometers, the thickness, and then also there has been some activities taken by AVE on the coating of the lithium metal surface. So all these materials together led us to the first generation of 1 ampere-hour cells. As I was saying before, this was a scale-up by CIDETEC, and they were able to manufacture more than 25 cells in order to be shared with all the partners involved on the testing. And what we found with this first generation of SAFELIMOVE solid-state cells were that we were able to have a pretty good result on cycling at 60 degrees, up to beyond 100 cycles, with a really good coulombic efficiency in all the cases. And if we translate this into energy density values, here we are summarizing in this table. So these are different replicates, so proving that the energy density calculated from the first discharge cycle, we can see how we were on the range of 240 watt-hour per kg and 400 watt-hour per liter. So as I was saying before, this was one of the really important milestones within the project because we were scaling up all the components and having the first generation of our 1 ampere-hour cells. As highlighted, as I was saying before, we were able to reach 100 cycles with these first prototypes, and then, again, the analysis of the interfaces post-mortem allow us to work on the next generation of materials. And mainly, we continue improving the coating of the cathode material. We continue working on the composition of the electrode, mainly with different additives, in trying to increase not the loading, so we kept constant the loading, but increasing the active material content. Of course, this having an impact on the energy density. And then, on the case of the electrolyte, we realized about some limitations when the different interfaces. So we designed a bilayer approach where we have a ceramic-rich phase or layer in contact with the cathode, while a soft polymer phase in contact with the lithium metal. And this was mainly guided by the results that we were obtaining from the previous generation. And now we are on the point where CIDETEC has assembled the second generation of 1 ampere-hour cells with all this new chemistry. The cells have been shared already with the partners, but we have some preliminary results. And if we compare here, I'm comparing the performance of the first generation SAFELIMOVE 1 ampere-hour cells with the second generation. We can see what we have increased around 15–20% the capacity that we are able to reach with this material. And this is mainly ascribed, or we ascribe to the tuning or engineering of the different components that will allow to have more stable interfaces. And the fact of decreasing the thickness, increasing the active material content, has allowed us to reach a higher energy density, both gravimetric and volumetric, in the range of 350 watt-hour per kg and close to 700 watt-hour per liter. Of course, there is still a lot to do on this regard. We really need to go further and understand how is the performance, how are the aging mechanisms, and how is the safety. But this is one of also of the second main outcome of the project. And finally, I wanted to summarize the challenges that we have faced during the project. I'm pretty sure that this afternoon during the session, topical session related to manufacturing, we will go again through this. But we have faced many challenges on the manufacturing of the solid state thick electrode. It's not really easy to reach these high loadings with a good performance. Then the manufacturing of the solid state hybrid electrolyte, so balancing ionic conductivity, so usually implies having a material quite soft, but if we translate this into an scaling up, so in a pilot plant, it's not so easy, so we really need to look for processable materials, and I think that the projects that will come after this, the ones that were granted with this cluster, I think that now we are going to be really aware about this issue, and we will need to have this in mind when we are designing the chemistry that we want to have within the cell. And as well, the manufacturing of the 10 ampere-hour cells actually was really a constraint, and for that reason, the upcoming results that we will have, it's going to be related to the cycling of 3 ampere-hour cells. So in order to be on the safe side and guarantee that we are able to scale up the technology, so from 1 to 3 ampere-hour cells, we decided to decrease a little bit the capacity. Cells have been manufactured already by SAFT and have been shared with the partners in charge of the cycling, so I hope to have some inputs or results soon on this regard. Also, safety, led by CEA, will be tested in this new generation of 3 ampere-hour cells. And also Ikerlan is working on the module design and on the validation. And this was all for SAFELIMOVE. Finally, again, I'm sharing the website, advertisement of the project, so go through it. And thanks a lot for your attention. Okay, so as I was saying before, we are missing the introduction the update for Solidify and Sublime, but we will have a coffee break in between, if I'm not wrong, I think. Yes, okay, just in case. And then afterwards, after these 2 presentations, we will have a session for questions and answers for the 4 coordinators. So we will be here, and please feel free to make as many questions as you want. So enjoy the coffee break. Thank you.